Hello students, in today's lecture we will continue our discussion on the torsion of the shaft, but we will take the specific case of the shafts which are in series or in parallel. Two dissimilar shafts which are made up of different material can be joined together to form a composite shaft, and these shafts which are joined together, they can be in series or in parallel. Now to analyze these shafts, let's start considering first the shafts in series. So as you can see here a figure in the figure that there are two shafts, the shaft 1 and the shaft 2, and they are joined in series. They have different length, they can be made up of different material, so their modulus of rigidity may be different, and as their cross section dimensions are also different, diameter is different, so in general their polar moment of inertia will also be different. Now this series shaft is subjected to a torque T at the free end. So driving torque T is being applied at the shaft 1 at the free end, and the resisting torque will develop at the fixed end. So there will be resistance which will develop, which is in opposite direction to the applied torque, that will be in the developed at the free end, and that will be also of the same magnitude but in the reverse direction. Now both shafts are subjected to the same torque but have different angular deformations. So the shaft 1 will be deformed, let's say, by angle theta 1, while the shaft 2nd will deform by the angular deformation theta 2. But they both will be subjected to the same torque T, because on shaft 1 you are applying torque T directly, and on shaft 2 there is a resisting torque developed of the magnitude, again of the same magnitude T. Now we know our relation that T by J is equal to tau by R is equal to G theta by L. So we will utilize that relation here. So T will be equal to, like if we apply for the first shaft, because T is same for the first and second shaft, so T will be equal to J1 times of tau 1 divided by R1. T by J is equal to tau by R. So T is equal to J1 dot tau 1 divided by R1, where tau 1 is the permissible shear stress value for the shaft 1. J1 is the polar moment of inertia of the shaft 1. R1 is the radius of the shaft 1. Similarly, because same torque is being applied on the torque on the shaft 2, so it will be equal to J2 times of tau 2 divided by R2. So that gives us our equation 1. Now because T by J is equal to also equal to G theta by L, so we will apply the same relation here for the shaft 1 and shaft 2, and this is going to give us G1 J1 theta 1 by L1 equal to G2 J2 theta 2 by L2. You see, the angular deformation in the shaft 1 is theta 1 and the angular deformation in shaft 2 is theta 2, and their net sum will be equal to the total angular deformation of the composite shaft or the joint shaft. So theta, the total deformation, is equal to sum of the angular deformation of the first and second shaft, theta 1 plus theta 2, and using the equation 2 you can write theta 1 as T1 L1 by G1 J1, and theta 2 you can write as TL2 divided by G2 J2. If the shafts are of the same material, so in that case their modulus of rigidity will be the same, and you can modify the equation 3 by bringing out the torque which is common outside, and G which is same, G1 and G2 will be equal to same because they are of same material, so G will also come out. So what is left is L1 by J1 plus L2 by J2 in the bracket. In case they are made up of different material but are of the same length, again the T and L are same, so from equation 3 you can bring out T and L outside, and what left in the uh, parenthesis will be 1 by G1 J1 plus 1 by G2 J2. So this is the case of series shaft. So what I understand from the series shaft is that the amount of torque that is applied in the case of series shaft is same for the both shaft, and the total angular deformation of the shaft will be sum of the angular deformation of the first and second shaft, theta 1 plus theta 2, right? So their torque is same but angular deformations are different, right? So that is what you need to remember in case of series shaft. Now let's come to the case of shafts in parallel. So here you have the two shafts, shaft 1 and 2, where the driving torque is applied at the junction of these two shafts, that means exactly at the middle of these two. So here where there is a junction where they both are meeting each other, the driving torque T is being applied here at this point. Because of this, there will be resisting torque that will be developed in shaft 1 and 2 both. So the applied torque T will develop the resisting torque at shaft 1 and as T1 and at shaft 2 and as T2. And total torque T applied torque will be equal to sum of the torque T1 plus T2. Okay. Now we have our relation T by J is equal to G theta by L. So let's utilize that relation. But you see here, though the applied torque T is producing torque T1 in shaft 1 and torque T2 in shaft 2, but their net deformation or the angular deformation in shaft 1 and 2 will be same. That will be theta, because we are applying the torque at the junction of it. So therefore the T1 will be equal to G1 J1 theta by L1 and T2 will be equal to G2 J2 theta by L2. So we will substitute these terms here. As I said that angular deformation theta will be same for both the shafts, so theta 1 will be equal to theta 2. You can also write from this for the, because T by J is equal to G theta by L, so from that you can write theta 1 as T1 L1 by G1 J1 and theta 2 as T2 L2 by G2 J2. From this you can find the ratio of the torque T1 by T2 as L2 by L1 multiplied by G1 by J2 dot J1 by J2. Okay. So if the shafts are of the same length, that means the L1 is equal to L2 by equal to L. So equation 4 can be modified. You can bring out the L common outside. Theta is already common for the same. So theta by L comes out to be, you are considering the equation 4. So you can bring out the theta outside and L outside, which is same. L is equal to L1 and equal to L2. So what left in the bracket will be G1 J1 plus G2 J2. So what we see in the parallel shaft is that the total torque, applied torque, will be equal to the sum of the torque in the produced in the torque shaft 1 and shaft 2, and their angular deformation will be same. Theta 1 is equal to theta 2 is equal to theta. Okay. So that is the difference between the series and the parallel shaft here. Let's do some numerical on this part. And what we have in this numerical is we have a stepped steel shaft which is subjected to torque T at the free end. So the free end is end C here, which is shown here as C. So at the free end you are applying a torque T in counterclockwise portion, and at the junction you are applying the torque 2T in the clockwise fashion. Okay. So at the junction of these two shafts we are applying torque 2T, while at the free end we are applying a torque T at the in the opposite direction. You see, this is the case of a series shaft, not the parallel shaft. Remember, though we are applying the torque at the junction of these two, but this shaft is not restricted at both the ends. It is only restricted at the point A, okay, not at point C. So that's why this is the case of a series shaft, and you are given the modulus of rigidity as 80 gigapascal here, and the maximum shear stress that is limited to 80 megapascal. So the material of the shaft is same for the part 1 and part 2 both. That means for section AB and BC the material is same, and their modulus of rigidity is 80 gigapascal and maximum shear stress that is allowed is 80 megapascal. You need to determine the total angle of twist. How much is the angle of twist of the composite shaft here? So the torque in the portion BC is, as I told you, is T in the counterclockwise direction. At this point we are applying the torque T in the counterclockwise direction. Torque in the portion AB will be equal to, as 2T it is being applied on the clockwise and T is being applied on the opposite side. So because of that the net resisting torque that will develop at point A will be T, and that too in the, because of the algebraic sum of these two, that means 2T minus T equal to T, that is counterclockwise direction, the clockwise direction. So we see here that the torque in the portion BC and AB both are same, but they are in opposite directions. So the maximum shear stress will reach the maximum value in the smaller diameter first, because you see T by J is equal to tau by R. Okay, so the value of J for the smaller shaft will be less, so that's why the value of tau will be higher for it. So therefore we will use this relation for the smaller shaft here. So smaller shaft is the shaft section BC, and for which the diameter is given as 40 millimeters. So we will substitute for diameter equal to 40 cube. Material permissible stress is 80. So that gives us the applied torque as 1005310 Newton millimeter, or 1005.310 Newton meter. Okay, so that is the value of torque that we have evaluated from this equation. Remember, here we have used the smaller shaft because smaller shaft will have higher amount of stresses produced, because the value of J for the smaller shaft will be less in comparison to the bigger shaft, or the larger diameter shaft. Now the angle of twist of the composite shaft will be equal to, because T is being applied in clockwise counterclockwise fashion, 2T is applied in clockwise fashion. So therefore the angular deformations for both of these are different, because in the section BC we have a torque T applied in the clockwise fashion, counterclockwise fashion. In the section AB we have just said that there is a torque of T in the clockwise fashion. So net deformation theta, angular deformation theta of the composite shaft will be the difference of the deformation in the section BC minus the difference of the angular deformation of the section AB. So because theta is equal to TL divided by GJ, okay, so we'll use this relation. Here we are going to substitute the length of the section BC and AB respectively, and the polar moment of inertia of the section BC and AB. Torque remains same for both of them because these are the case of the shaft in series. So we substitute the value of torque here T, the value of modulus of rigidity as 80 into 10 to the power 3. For the polar moment of inertia pi by 32 we have taken out as common, and what remains is the d4. So the diameter to the power 4 for the section BC is 40 to the power 4, and for the section AB is 60 to the power 4, and the length of the section BC is 1500 as you can see here, and length of the section is AB is 1 meter, so 1000. You substituted all these values here and calculate the angular deformation in radians. So that comes out to be 0.065 radians, and if you multiply it by 180 by pi, you can obtain the angular deformation in degrees for it. So that comes out to be 3.73 degree. Let's look at another numerical. So here we have a bit complex case. Here you are given that a torque of 2.5 kilonewton meter is being applied to the composite shaft through a rigid plate. So you can see here is a composite shaft. So you have a hollow shaft of aluminium. Okay, so this is the hollow shaft here of aluminium here, and inside it there is a solid shaft of brass given. The diameter of the brass shaft is 16 millimeter. The hollow shaft aluminium is having outside diameter as 48, inside diameter is 32. Okay, so on one side of the rigid plate you have a hollow aluminium shaft and encasing the brass shaft inside it. Okay, and then on the right hand side of this rigid plate you have the steel shaft. Okay, so this steel shaft is also a hollow shaft with the inner diameter of 24 millimeter and outer diameter of 32 millimeter. So this is the construction of our composite shaft here. So on left side there is aluminum plus brass, and the right side there is a steel, and this is fixed at section D at point D, and steel shaft is fixed at point D, and aluminum plus brass shaft are fixed at point C. We are applying a torque of magnitude 2.5 kilonewton meter on the rigid plate. Now because of this, there will be fixing torques that will be developed at section C and D, which we are going to talk about in a moment. In this question you need to determine the maximum shear stress in the each material. So in order to determine the stresses values in the each material, we need to determine the value of torque that is shared by each of these shafts. That means how much torque is being applied on aluminum shaft, how much is on brass shaft, and how much is on steel shaft. Applied torque is 2.5 kilonewton meter, out of which what portion is being shared by each of them, that we need to work out, and then we can easily calculate the maximum shear stress for each of the material by simply using the formula. First, let's calculate the polar moment of inertia for all these three sections. That is very easy. Pi by 32 d4 for solid shaft and pi by 32 d for outer 4 minus inner 4 divide will be equal to for the hollow shaft. So you substitute the value for brass, steel and aluminum respectively, and their dimensions you will substitute here. For brass, steel and aluminum, you can calculate the value of JB, JS and JA for brass, steel and aluminum respectively as shown here. Now, because of the applied torque at the rigid plate, the rigid plate will rotate, let's say, through the angle theta. Now this theta shall be same all for aluminum, brass and steel because we are applying exactly at the junction. So in that case, the angular deformation theta will be same for all these three. But the applied torque will be resisted by opposite torque at the two ends, which will be termed as fixing torque. So there will be resisting torque at point C, resisting torque at point D, and their net sum will be equal to applied torque. TC plus TD will be equal to 2.5 kilonewton meter or 2500 Newton meter. So let's say the fixing torque at D is TD. So that means the fixing torque at C will be given, TC will be given as 2500 minus TD. Now this fixing torque at C, which we are talking about this point, so this fixing torque will be shared by aluminum and brass both. So that we need to see. Now as it is shared by both brass and aluminum, so TB plus TA will be equal to TC, that is TC is 2500 minus TD, which we have just calculated here. So TB plus TA will be equal to 2500 minus TD. And what is the TB or what is the TA? You can express T by theta is equal to GJ by L. So angular deformation theta is same. So that's why theta times of GA, JA by L will be TA. And similarly theta times of GB, JB by L will be equal to your TB. So torque applied at brass and torque applied by at aluminum. You bring out theta and LL common outside this, so that remains theta by L equal to GA, JA plus GB, JB. From this you can calculate the angular deformation theta as 2500 minus TD into L divided by GA, JA plus GB, JB. Now this angular deformation theta we have calculated from the left hand side of this rigid plate. On the right hand side there is a steel shaft which is also having the same angular deformation theta, and if we use the relation T by theta is equal to GJ by L for that part, so that gives you theta is equal to TD. TD is the amount of torque in the steel shaft. You see here TD is the amount of torque that is shared by the steel shaft, fixing torque at D. So that is completely taken by the steel. So that's why I have written here as TD. So theta will be equal to TD times of L divided by GS. You equate the equation 1 and 2, and after doing little bit of mathematical manipulation or substituting the value of GJ that you have already given in the question, you can calculate the value of TD as 832.9 Newton meter, and the value of TC will be 2500 minus TD. So that is calculated as 1667.1 Newton meter. So this is TD that is calculated from the above calculations, and TC is applied torque minus the fixing torque at D. So 2500 minus TD, that comes out to be 1667.1 Newton meter. Now as I have just told that the fixing torque TC is shared by both aluminum and brass. So TA plus TB is equal to TC. So TA can be written as TC minus TB, that is 1667.1 minus TB. Besides this, we know we can define the TA by TB as GJ theta by L for aluminum shaft, GJ theta by L for the brass shaft. You substitute the values here. Angular deformation theta is same for both the shafts and length is same for both the shafts, so that will get cancelled out. So theta by L will get cancelled out. What remains is GA by GB. You substitute the value of GA, JA, GB and JB here, and you can calculate the ratio of TA by TB as 43.875. So you have one equation in TATB here, equation 3. Another equation in TATB is equation 4. Two equations, two unknowns are there. You can compute the value of TA and TB as 1630 and 3371.9 meter. So now in this case we know what is the amount of torque shared by aluminum shaft, brass shaft and steel shaft, which is TD. So once we have got the values of torque that is being applied in these shafts, we can calculate the shear stresses by simply using the formula T by J is equal to tau by R. R will be equal to D by 2 here in this case. So we know that for the solid shaft the formula is tau is equal to 16 T by pi d cube. So 16 torque on the brass shaft is 37.1 into 10 to the power 3 Newton millimeter, and that equals to pi d into 16 cube. The diameter is 16 millimeter. You can get the values of tau b as 46.1 megapascal. Now aluminum and steel shafts are the hollow shafts, so you substitute the values here for the hollow shaft, the polar moment of inertia for the hollow shaft, and you divide it by the d by 2 of the outer diameter. So that gives you 16 t into d divided by pi d4 minus small d4, and you substitute the respective values here, and you can compute the value of amount of shear stress produced in the aluminum shaft and steel shaft as shown here. Now let's do one more numerical, and now we have a case of a compound shaft as shown in figure. It is made up of half part is made of aluminum, another half is made up of brass. They both are of same length 500 millimeter, and they both are of the same diameter 40 millimeter. The torque is being applied at the free end, so it is basically a case of a series shaft, and you are given the modulus rigidity value for the brass and aluminum as 34 and 28 gigapascal, and the maximum shear stress that can be produced or registered permissible stresses are 78 megapascal for the aluminum and 55 megapascal for the brass. Besides this, you are given that the maximum angle of twist of the total shaft should not exceed by 3 degree. What we need to calculate? We need to determine the maximum torque that you can apply on this shaft. You see, the maximum torque will decide how much power it can transmit. You must have remembered in the last class we had the power formula 2 pi nt by 60. So the amount of torque that this shaft can carry will decide the amount of power that it can transmit. So the maximum torque that can be applied through this composite shaft need to be calculated. First thing that we'll do is to calculate the polar moment of inertia, which will be same for both part A and B. So aluminum and brass both pi by 32 d4 you calculate here as 80 into 10 to the power 3 pi millimeter 4. Now first we will use the permissible value of shear stresses to calculate the amount of torque that can be applied, and for this we will use the relation T by J is equal to tau by R. And first let's do it for the brass. So for the brass, T is equal to tau B into J by R. J is, we have just calculated the value of J here. Radius of the shaft is 20 millimeter because the diameter is 40. Permissible value for shear stress is 55 megapascal, which is given in the numerical. You calculate the value of torque from this as 691.150. You apply the same formula for the aluminum shaft, and for the permissible value of tau A, this time you will substitute 78 megapascal, and you calculate the value of permissible torque that can be applied in this case as 980.117. Now apart from this, you are also given that the maximum angle of shift allowed or permissible is 3 degree. So because it is a case of a series shaft, so let's use the series shaft formula theta is equal to theta 1 plus theta 2. So for the aluminum part, theta 1 will be given by T times of L divided by GA. For theta 2 part will be T times of LB GB. You have T, L and J common for both the shaft length, and polar moment of inertia is same, and as well as the torque applied is same, so you bring it out common, and you can have the 1 by GA plus 1 by GB here. Using this formula again you will compute the value of torque T. This is time it will come out to be 404.1209 meter. You see, amongst the three values that we have calculated, 691, 980 and 404, this is the least value. So because we need to choose the least value amongst them, which will be maximum permissible value. So the maximum amount of torque that this composite shaft for the given restrictions it can transmit is 404 Newton meter. Okay, so this brings us to the end of our chapter of torsion. In the next lecture we will start the new chapter.